In this video, we will continue to talk about alkane nomenclature, this time focusing on cycloalkanes. Before we start naming our cycloalkanes, I wanted to mention the general formula. Keep in mind for alkanes, the general formula is CnH2n plus 2. Well, for cycloalkanes, the general formula is CnH2n. So we are 2 hydrogens short, which means a ring is a type of unsaturation. When we're naming cycloalkanes, we use the same base names as the regular alkanes, but then we include the prefix cyclo to specify that the carbons are in a ring. So where we have 1, 2, 3 carbons, a 3-carbon alkane would be propane, but we have to specify that these 3 carbons are in a ring, so this is cyclopropane. Cyclo tells us it's a ring, the prop tells us it is 3 carbons, and the ane tells us that all of the carbon-carbon bonds are single bonds. If we have 4 carbons, this would be cyclobutane. 5 carbons, this is cyclopentane. 6 carbons, cyclohexane. 7 carbons is cycloheptane. And 8 carbons, perfect that I got back to red, this is cyclooctane, our stop sign. Notice we have cyclo and then octane, so it's 2 O's, cyclooctane. Now, if we have a ring that has a branch, typically we want to focus on which one is bigger. Because this is big and this is small, we're going to name this as our base and then this is our branch. Over here, because this is big and this is small, it'll be easier to give this the base name and call this a branch. So we have 6 carbons in a ring, so this will be cyclohexane, and then this is a methyl branch. So this first compound is methyl cyclohexane, all one word, methyl cyclohexane. Now remember, if we had a branched alkane, we had to specify where the branch was. But here, if there's only one branch, we don't have to specify the carbon, because if there's only one branch, that is automatically at carbon 1. So that saves us the huge effort of having to write 1 and a hyphen. So you're welcome. Next, we have, again, cyclohexane, and we have 2 branches. They're both on the same carbon, but we do have to specify. This is going to be 1,1 dash dimethyl cyclohexane. So we have 6 carbons in a ring, and then at carbon 1, we have a methyl group. Also at carbon 1, we have another methyl group. For the next one, we have methyl branches again, but now they are on adjacent carbons. So we have a few options. We could number clockwise 1, 2, 3, 4, 5, 6. We could number counterclockwise 1, 2, 3, 4, 5, 6. Or we could number counterclockwise but start at a different position. So this could be 1 and 2. So numbering the blue way, that gives us the substituents or the branches at carbon 1 and carbon 6. That's not good. If we number the red way, that gives us our methyl branches at carbon 1 and carbon 2. The green way, carbon 1 and carbon 2. So it doesn't matter whether we're doing it the red way or the green way, it ends up the same thing. So this one would be 1, 2 dash dimethyl cyclohexane. Now with this one, we have 2 substituents again, 2 branches, but this time we have a methyl branch and an ethyl branch. So this time it does make a small difference which way we number. We want to make sure we are giving our branches the lowest number possible. So we could potentially call this 1, 2, 3, or we could go a 1, 2, 3. Now, either going red or blue, we would still have our substituents at carbon 1 and carbon 3. So the tiebreaker is that you would then number them alphabetically. Yes, we are numbering alphabetically. We number the substituents as they are listed alphabetically. This one is an ethyl branch, and this one is a methyl branch. So we're going to give ethyl the lower number. So this is carbon 1 and this is carbon 3. So this one will be 1 dash ethyl dash 3 dash methyl cyclohexane. Methyl cyclohexane is one word. I just don't have enough room. 1 ethyl, 3 methyl cyclohexane. In our next example, we have 8 carbons, and then we have a 3-carbon ring that we can call a branch. So our base name would be octane. We number from left to right to give our branch the lowest number possible. And then we have to name our branch, and we use the same approach where the cycloalkane becomes a cycloalkyl group. So this would be a cyclopropyl substituent. So the overall name is 2-cyclopropyl octane, all one word. 2-cyclopropyl octane. In our last example, this is 9 carbons, this is 6 carbons, so we should go ahead and number this as our base and then this is our branch. But even if it was a little bit different, trying to name this as a branch would be difficult to do, and so naming this as a branch is a lot easier. So as a branch, this would be a cyclohexyl, and then we would want to number our chain starting here. And so this compound would be 4-cyclohexyl nonane. We have a 9-carbon chain. Branched off of carbon 4 is a cyclohexyl group. This takes care of the basics of naming cycloalkanes. Now, we did see earlier in this chapter that we can have bicyclic systems, fused or bridged. There are systematic approaches for naming all of those, and you can use your textbook as a reference for naming those types of compounds. So it turns out we're not completely done with naming cycloalkanes. Let's consider for a moment 1,2-dimethyl cyclopropane. And let's compare this to butane, which I can write CH3, CH2, CH2, CH3. Now, these are all sigma bonds, and so with a sigma bond, we can rotate around the bond freely. So imagine if you were rotating around this bond, you could bring this methyl group coming forward, and then you could rotate as well and bring this methyl group forward. But you could also rotate it back the other direction so that, so that instead you could have this methyl group going back. And you can make these changes without changing the compound itself. You're changing the arrangement in space, but it's still the same compound. But when we have a ring, even though these are sigma bonds, we don't have free rotation around here. This carbon, we have a methyl group, and we also have connected here a hydrogen. And then over here, we have our methyl group drawn. We also have a hydrogen. Now, it's possible that this methyl group is coming forward and this hydrogen is going back. This methyl group could be coming forward and this hydrogen is going back. But it's also possible that we have this methyl group coming forward and hydrogen going back, but over here, maybe we have the methyl group going back and the hydrogen forward. Now, the difference here is different than what we have in the case of a straight chain compound. Here we can rotate freely, and so we could move this forward, we could move this forward, move this back. It's the same thing. But here we cannot interconvert this compound to this compound just by rotating around a single bond. So even though they have the same connectivity, the groups have a different arrangement in space, and they cannot be interconverted by rotation around a single bond. So these compounds are actually isomers. They are different compounds which will have slightly different properties. Now, we talked previously about isomers, and we know that isomers have the same molecular formula, but are different compounds. So far, what we've seen are constitutional isomers, where we have different connectivity. So if we have 4 carbons, we could have them connected in a chain, or we could have them in a 3-carbon chain with a methyl branch, right? These are constitutional isomers because there is different connectivity. This carbon is connected to 3 other carbons. We don't have any carbon here that's connected to 3 other carbons. But over here, this carbon is connected to 1, 2, 3 carbons. This carbon is connected to 1, 2, 3 carbons. So they have the same connectivity, and yet they are different compounds. So here we have an example of stereoisomers. So stereoisomers have the same connectivity, but a different arrangement in space. So because these are 2 different compounds, we need to provide unique names. And so what we use is cis and trans. Cis means that our similar groups are on the same side, and trans means that our similar groups are on the opposite side. So looking at this ring, this is going to be in the plane of the screen. And so we have a front face that's in front of the screen, and we have a back face that's behind the screen. In the first example, both methyl groups are in front of the screen, and so here our methyl groups are cis to each other. Whereas in this one, this methyl group is in front of the screen, and this methyl group is behind the screen, so this would be trans. So on the previous slide, we named these 2 compounds as 1,2-dimethyl cyclohexane, and this one was 1-ethyl-3-methyl cyclohexane, but that's not specific enough. For the first one, we could have both methyl groups coming forward, and this would be called cis 1, 2 dimethyl cyclohexane. Or we would have this compound where this methyl group, for example, is coming forward and this methyl group is going back. This one would be called trans 1, 2 dimethyl cyclohexane. With this other compound, we could have our ethyl group coming forward and our methyl group coming forward. And so this one would have a prefix of cis, or we could have our ethyl group coming forward and our methyl group going back. And so this one would have a prefix of trans. So it's important to look for the possibility of cis-trans isomers, as a type of stereoisomers. They will have different properties, and so they need to have distinct names.